Welcome everyone to retronetcall tonight. The topic is Group 4 Facsimile Service, or in short, Fax G4 or G4 Fax or Group 4 Fax, or whatever you want to call it. I'll start with introducing the topic. A little bit of history on previous fax services, then what is different in G4 Fax. We look at the protocol stack and at protocol traces to get an idea how this works. The Facsimile Service, as specified by the International Telecommunications Union, goes back well into the 1960s. Of course, there were previous facsimile devices, I think going back almost as far as telephony goes back. So there have always been some systems that were capable of transmitting images, of course, extremely rare, maybe used in, I don't know, military applications or I don't know, but certainly not in commonplace and outside of some serious government offices, newspapers, as Nibbler points out. Yeah, thanks. Then the ITU did the first specification on telefax machines in 1968, or on the so-called Group 1 fax machines. Didn't really study a lot about it. It's also not the subject of the talk. So suffice to say that it was 6 minutes per page. And I think it's even was analog transmission and not digital. But as I said, I really don't have any clue about this, so I better shut up. A couple of years, almost a decade later, in 1976, Group 2 was specified, halving the transmission speed for a page. I guess page, not sure, I guess always refers to an A4 page. In G4, we have different page sizes. Christoph says, yes, it's a frequency shift keying or frequency modulation of the gray value. So indeed, analog transmission. There was, interestingly, despite ITU specifications, apparently there was no universal interoperability yet. So you had to have usually the same devices or at least the same manufacturer at both ends, which I find a bit weird given that, well, what did they have specs for? But yeah. Not really the topic of today. G3 is a bit more important since we need to differentiate how G4 relates to it and what is different to it. I guess G3 telefax is what most people are familiar with. It was specified originally in 1980, and it was the first truly interoperable standard where you could mix and match different vendors of fax machines. The transmission speed was less than 1 minute per page. That's what was advertised. It uses a modem to modulate digital pixel data, or I think they call it PEL data, PEL, the picture element, over a PSTN network. So I think even initially, at least in some countries, separate networks that were not the PSTN network for whatever reason. The transmission speeds initially 2,400 to 9,600 bps, but later upgraded up to 33,600 bits per second over analog modems. Now, of course, you could do G3 fax like any other analog telephony or analog service that used the PSTN. You could also use that over ISDN, and you can. But actually, very few. Well, oh yeah. Sorry, forgot I had this picture. I found that online. It's this, not 1998, but yeah, sorry. I should have checked those slides. It was 1981, actually. So 1 year after the G3 specification came out. This is a fax machine from 1981, a small one at the time, apparently. Weighing only 70 kilograms. So yeah, that's a very nice small fax machine there. So only, oh, my year numbers, it's horrible. 1985, of course. So 5 years after the G3 fax was specified in 1980, I will fix up those slides later. 5 years later, the G4 fax was specified. It was not strictly specified for ISDN, but it was intended as a general digital telefax service to be used over any kind of data network or digital network. And it's specified over the CSPDNs, circuit switch public data networks, using X21 interfaces, also over PSPDNs, packet switch public data networks with X25. If you want to hear more about CSPDNs, there was a previous retronetcall on this topic, and also over ISDN, which in 1985 was not really was bleeding edge basically, whereas the other two have existed. I'm not sure how much G4 fax, if ever, was used over CSPDNs or PSPDNs. I'm very happy to receive related pointers or information. It was deployed over ISDN, but also only to a very limited extent. The difference to G3 is mainly it's a fully digital system, so there is no modem involved. It just defines how bits of digital data get from A to B, and hence it also cannot operate over analog telephone lines, at least not like an analog PSTN service over an analog telephone line. Of course, you can use some kind of something like an ICUT or whatever, some device that modulates stuff over an analog telephone line, but the fax service itself is not specified over a modem as such. And you couldn't use it with an analog PSTN connection. What kind of capabilities does G4 have? The black and white service is mandatory. A grayscale and color is optional. There's a couple of different resolutions specified, 200, 240, 300, and 400 pels per 25.4 millimeters. This is really how it's specified. Is fancy ITUT language for dots per inch. If you look for the definition of PEL, you will, I think the only references you find are some old IBM manuals. Apparently it's a historic term that was used before pixels or DPI was used in printing. So also interesting, I never knew about this before reading the specs recently. G4 fax actually also has optional file transfer capabilities. So you can transfer files without or with metadata, and even edifact, that's basically business data formats between companies, was specified. So there's a bit of overlap with the FTAM, the ISO-OSI file transfer that was also used in ISO-OSI networks or Eurofile transfer and so on. But yeah, for some reason it was also specified over G4, which I guess with a physical fax machine doesn't really make much sense. Then a fax machine would have had to include a floppy drive to make use of this. So I've never heard of this. Again, if anyone has pointers on this, I'm more than happy to hear about it. I guess it's more useful in the context of software G4 fax implementations, where then you could send a fax and some EDI data together over between two software G4 fax implementations. I'm not sure if anyone has implemented or used it. I find it rather exotic. So I tried to dive into the specifications of G4 fax, and it is comprehensive to say the least, and it is unfortunately very convoluted, because you have probably about a dozen, this is not all of them that I list here, probably about a dozen of different specs pointing to each other, and none of them really clearly specifies what exactly is used. They all specify all kinds of things that could or could not happen, depending on the underlying transport. And since it's not specified as transmitting fax over ISDN, but it's specified as transmitting fax over some kind of random data network, it's all very abstract and very loosely interconnected. So we have the T563 specification, which is the terminal characteristics for group for facsimile apparatus. This spec is sort of the entry point. If you want to look at those specs, it then points to many of the others, such as T6, T81, T82, T70, T62, and T90. I'm not going to read all those definitions, but that's sort of what they include. The main ones we will be looking at is the T70 and T62, indirectly through T90. But when you start looking at this, basically it looks like this. So you read the core spec, the T563, which by the way includes references to other specs which have been withdrawn meanwhile. But among others, if you think of ISDN, you will find, oh, it points to T.90, and specifically Appendix I of T90 for ISDN, and then you check the T90 specs, which states that different ISO specifications from the X25 family are used as layer 2 and layer 3. And it also includes all kinds of exceptions to those X25 specs, like that there are no empty iframes on transmit, but they should be ignored on receive, whereas the original X25 specs, which include X75, permit such things. And yeah, so it also includes an important statement in Appendix 2, T70NL, where T70 is a protocol that you may have heard of before if you're following this series of retronet calls. We'll look at this later. So how does it look like from the ISDN side? Well, if we establish the call first, we establish normal D-channel signaling call control using the Q931 as layer 3 or over Q921 again. Oh my God, I should look at this again. I was so trying to finish the Wireshark dissector, I didn't reread the slides, which apparently was a really bad mistake. So yeah, we have the usual Q931 layer 3 on ISDN D-channel. It's just signaling it. The bearer type is UDI, unrestricted digital information, or I guess in the US RDI, restricted digital information. And optionally, you can have a high or low layer capability element that tells you it's fax, but I think that's not really mandatory in the spec. But yeah, it basically looks like any other data call over ISDN with a transparent channel, 64 or 56 kilobits. So in that B channel, then we use X75, which is also a protocol that's quite commonly used inside ISDN B channels. Again, there was a previous talk on ISDN B channel protocols that mentions this. X75 itself is also not an ISDN protocol, but it is a protocol that was originally specified as a interworking protocol between different X25 networks. So X25 is the user-facing interface of an X25 network. And if multiple different X25 networks, also called PSPDNs, interconnect, they use a protocol called X75. And that protocol, for whatever reason, people thought it's a good idea to reuse that over ISDN B channels in a much more simplified way because, well, of course, you don't have hundreds of thousands of users on either side of the link, but only one. So there are some simplifications, and also it's only a single link procedure, so only a single B channel and so on. And inside this X75, which is a derivative of the old HDLC family of protocols, very similar also to the Q921 LabD protocol on the D channel, so basically it is a protocol that provides us with acknowledgements and retransmissions of packets that got corrupted, and it includes CRC16 checksum of every message. So it provides us protection against corruption and or lost messages, reliable transmission basically. And then in the user data field of the X75 data, we have this T70 protocol. They always say T70NL, and like there is only a T70 specification, and with NL they just mean, well, it implements the network layer of the ISO-OSI layer model. And then inside T70, we will look at what T70 does in a few minutes. We then have this T62 protocol. And in case you have heard about these acronyms before, yes, exactly. The same stacking with T62 over T70NL is what is used in teletext, not teletext, and not telex, but teletext, this weird intermediate system between telex and telefax, about which there also was a retronetcall last year that you can look at. So there's a lot of common functionality between teletext and G4 telefax, which makes sense if you think about it, because in the end, well, both are about transmitting pages of text from one location to another. The only difference is that in the instance of teletext, it is characters of formatted text. And in the case of telefax service, it is pixel data. But this entire concept of exchanging identities and setting up a reliable transmission and signaling start of page and end of page and page boundaries and page formats, paper formats and whatnot, all of this is exactly the same in both use cases. So it's actually rather logical that you can use the same protocols and just change the payload. So if we look at T70NL, it only really consists of 5 different types of blocks that are transmitted. There's the transport connection request block, there's the accept block, so that's basically your initial handshake when the connection is set up. The connection clear block is to tear down the connection, and we have a generic reject, the TBR, transport block reject, which is used to reject any of the messages. And last but not least, we have the TDT, the transport data block, which then contains user data. I think it's, yeah, we will look at how those messages look like. So you have a couple of bytes of header for each of those block types. Unfortunately, the header length depends on the block type used. I think for transport data, it's a 5-byte overhead or so. For all the others, it's much larger. Yeah, and now, but yeah, it doesn't really do much, this T70 layer. In the end, the main functionality is within this TDT, which also performs segmentation. So TDT so we have the X75 that provides us with a reliable transport channel at that layer, and in that we put the T70NL TDT blocks, and those provide segmentation and reassembly. I think the TDT at this layer, T70, I think 128 octets or so is the maximum, and larger messages contained in T70 then get segmented over multiple TDT blocks. There's no CRCs or protection or whatever at this layer, because this is all handled by the X75 below. Now the T62, that's really what nothing up to this point relates to fax or transmission of pages or text or pixels or anything. This is all just transport stuff, network protocol, transport stuff. And now in T62, we have a protocol layer or rather a protocol that has 2 layers, the session and the document layer. And some concepts. So we have pages, which are, well, basically scanned pages in case of telefax. A document is a collection of pages, and a session is used to transfer documents. Sessions are unidirectional, and to transfer documents in the return direction, you need a new session. The calling party is the session master, the called party is the session slave. Initially, at least, the calling party is the document master, but there's a command that can swap roles using CSCC command. That's what you would have used for fax polling. So if basically, normally when you send a fax, then you call some other number, and you as the caller are transmitting the page, but then there's also fax polling, where you call some other system which then transmits a document to you, and this is basically why they have this command to swap the roles in the T62 session layer. Now the session layer has a number of different messages or packets. They all have rather strange acronyms, at least if you're not coming from this specific pocket of ITU, telematics and fax and teletext. The way how to read those is you don't read them from the front and you don't read them from the back. I mean, so far I know acronyms that you read from the front or from the back. No, in case of these T62 acronyms, you always have to start with the middle two characters. This will tell you what this command is about. And then you can look at the start or the end to tell you sort of which flavor it is. So we have session start here, SS, and the C in front means it's the command for session start. And if we have an RSS, then this is a response for the session start, and P is a positive response, and N is a red negative response. So always start with the middle two characters in order to, or sometimes I guess 3 characters, to know what kind of a command it is. So C and R in the beginning is command and response. At the end, P and N means positive and negative in case it's a response, and the medium characters, middle characters tell you what this is about. So CSS, RSSP, and RSSN is to start up a session. CSE to end the session. RSEP is the response positive. There is no negative response. I guess it's not possible to reject the end of a session. So that's why there is no negative response. There's also an abort for an abnormal termination, which also, again, only has a positive response. You can't sort of decline an abnormal termination. The other few messages at the session layer is the SU, the session user, or SUI, session user information. Again, that has a command and a response. And then we have the CSCC from the previous slides. This is the session change control using which you can modify the direction of the document master versus document slave role. And that again also only has an RSCCP, the response session change control positive, that you can answer to that. And beyond the session layer, then you have documents. That's actually what you want to transmit. And for documents, again, the acronyms are parsed in the same way. It's a little bit less regular. So we have the document start and the document continue. Both are commands. We have the response document general reject as some kind of general not acknowledged message. And then there's a document capability list command and response. I guess this is again just a typo of mine. I will clear up those slides after the talk is over. Command document end, again, which gets positively acknowledged. We have a discard message that can get acknowledged. And last but not least, the CDUI, the command document user information. That's where your actual pixel data or your compressed pixel data or PEL data in language of the specs will go into. There's also a command for page boundaries here between pages, which again gets only positively acknowledged. So that's in T62. And then there's a couple of more additional, I think maybe only 2 I've seen in protocol traces. There might be more. I didn't look at the specs that deep, but there are a couple of more, let's say, fax specific commands, how T62 got extended in that part. So this is all very theoretic and lots of different messages. So let's look at some actual protocol traces. How does this look like? Well, how do we obtain a protocol trace? Well, we need to obtain some G4 fax machines and transmit pages. This is what Mana, Worm, and I have done a couple of days ago. I have recently acquired one of the few and rarely sold second-hand, or I don't know, maybe even fifth-hand G4 fax machines. So it's a physical fax machine, a laser fax machine from Canon. It has an ISDN basic rate interface, and I set this up, and Mana Worm was using a software fax implementation on Windows. I think it's called RVS fax. And then we exchanged some pages of documents. And interestingly, now how do we get a protocol trace? Well, there's actually an option in the Canon fax machine which can print you D-channel and B-channel protocol traces after you completed a fax transmission. then you get a protocol trace on paper. So that's 1980s Wireshark, even though the fax machine is from 1999. And of course, in our own network, we can also do raw B channel traces and then decode those with software further up the stack. So this is a scan of a printed protocol trace of an actual fax that we transmitted. You can see it was on the 4th of March at 1:40 p.m. German local time. And if we look at the beginning, so one thing to notice about this trace is that it completely mixes the different layers, and the hex dumps you see are only the one, like the layer that it shows here. So SABM is of course the set asynchronous balance mode. So the way how a X75 connection is set up, we see there's a retransmission because it's not immediately acknowledged, probably because we have delays in our software ISDN over IP network. So we see a retransmission of that. And the 013F is actually the hex dump of this SABM command. Then we see the unnumbered acknowledged, the 0173. That's the answer of the remote end to the SABM. So from this point onwards, we have the layer 2 connection, the X75 connection established. There are CRC values after all these messages, which are skipped here by the fax because it only shows us correct messages with correct CRC, and there's no point in displaying it in the protocol trace. Then there's some commands that I actually do not know what they are. We see this SQ and SF. I haven't found the spec for these yet, so I also don't know what they do. If anyone does, please let me know. Next, we have CR and CC. That's, well, connection request and connection confirm. And we actually see here this 10.00 and 10.01. These are actually header values of the, now I have to think again, that's the, I think the T70. I have to think again and look at the specs. Yeah, I don't want to make a wrong statement. We will look at this in detail later on. So the TCR and TCA, those are definitely two T70 commands. We saw them in the earlier description of the T70 command. So the transport connection request and acknowledge, I guess. We can check again what the meaning was. Accept, yeah. So transport connection request and accept. That's our T70. And in the dump of these messages, the fax machine already skips the underlying protocol, meaning the X75 that is actually in front of this, and just displays us the T70 message here. And the accept for that, and then we see the CSS. That's the what was it? The command session start. Already one layer higher. So this is the first message from the T62 layer. Again, of course, with the T70 in front and the X75 in front, which is not shown here in the protocol trace. We only see the T62 message. And if you look a bit into this message, you can actually see here 34, 39, 33, 30, 31. So if you know ASCII code, then 30 hex is start of the decimal digits. So we actually have 49301234. 2152 here. So that is the phone number of my fax machine here in my home office. So we can see already that the identities are in here. And later in the message, you also see another one, I guess is the called party. But yeah, this is encoded in this message. Yeah, if we look further down, when this is the response from the other side, oh yeah, in the response, of course, there would be the other side, the other party. So again, yeah, we have 49 space 306502 02141. Yeah, that's the Manaworms fax number that we used in this exchange. So the trace continues. Then we have the CDCL. Well, that is some, I have to check again. Command document capability list and the response to that, the RDCLP, the response to the capability. So the two fax machines or fax implementations exchange their capabilities in terms of color, black and white, page sizes, things like that, compression schemes, whatnot. And then we have the CDS, that's the document start, so command document start, which gets followed by a P start. So all of these messages are T62 messages. The P start then is a telefax specific message, not specified in T62, but following T62 format. P end is the page end. And then we have CDPB, that's the command data page boundary, which gets acknowledged by the other send. We have another P start and P end, so the second page of our fax transmission. Then we have the command data end, command data, response data and positive document, sorry, command document end, response document and positive, and finally the command session end and response session end positive. Then again, we have this CQCF, which I don't know from which spec it is. And in the end, we have an RNR frame because the receiver was not ready. So there's some retransmission at layer 2 happening. But yeah, that's sort of a transmission of 2 pages in this protocol trace. The actual page data is not shown here. Obviously, it would just be pages and pages full of hex dumps for all those pixels. So between the P start and the P end, you have the actual page data with the pixel information for the fax. Yeah, that's it as far as my presentation slides go. I can show you a bit more protocol traces in hexdump and partial dissection in Wireshark. But before I do that, let me put a quick break in case there are questions on, let's say, the introduction or the theoretical part so far. Yeah, Eric, hi. Yes, I'm aware that, of course, ISDN was very rarely used in the US, but even in Germany, where ISDN was extremely popular, ISDN G4 fax never took off. It was very rare. There were very few machines that supported it. Even those fax machines, or many of the fax machines that had an actual ISDN connector in the back, it were just G3 fax machines with some integrated terminal adapter that converts the internal, let's say, PSTN line that never left the fax device to an ISDN line coming out of it. So it's a rarity even over here where ISDN was popular. And there's a question from Michaela who says there was only one physical G4 fax machine in this test setup. What was the other end? It was a Windows machine with, I guess, yeah, exactly, Windows XP machine with RVS.com RVS fax, which is a software G4 fax implementation. That was the other end here. We do have one member in our community who has another G4 fax machine, but he hasn't set up his connection to Octo yet, or the PBX is not configured yet. So I guess in the next few weeks or months, we will also be able to do it between 2 actual physical fax machines. But I only have one of those G4 capable fax machines here, so it was a software fax implementation to a hardware fax. Yeah, so there's a question about how that Windows software talks to physical ISDN. Well, Michaela, you have an ISDN adapter in your PC, and those can, of course, be ISA cards or PCI cards or yeah, PCMCIA, USB, whatever. And then there's there's actually multiple, but sort of the more popular standard software interface, how ISDN application programs can talk to ISDN hardware. It's called CAPI, the Common Application Programming Interface, I guess. And using this interface, you can basically mix and match any ISDN hardware with any ISDN application software. So that's the usual setup. It's basically the same setup you would have used, for example, to make ISDN dial-up calls from this PC, just that you use a different software. So you don't use the whatever was the dial-up network name in Windows at the time, I don't know. But instead of using that, you would just use another program that then uses this ISDN for fax connection. Yeah, and you have transparent B channel access if you want on any of those ISDN adapters. So yes, you can do voice, you can do fax, you can analog fax if you have a soft modem implementation, G4 fax if it's digital. You can do V110, V120, and so on and so on. Yeah, you can. Manavam, yes, Manavam is suggesting that we should install the English version of all that fancy German ISDN software somewhere and show that. Of course, by all means, you can do a retronet call on that. I guess you have some kind of frame grabber for your Windows device, VGA output or whatever it might be, or it's maybe even a VM or something. Yeah, if you can get that. Yeah. So in any case, let's maybe continue the topic. I hear there are other questions about ISDN devices, but that's maybe something for the more generic discussion after the actual topic is completed. So yeah, let me quickly switch over to away from the browser to a manually annotated hex dump if I can find the respective window in my chaos of way too many open windows, and share that. So just a second. So this is the first step when I looked at try to decode these messages. I actually just ran the raw B channel trace. That's a bit stream. I ran that through through a software HDLC decoder. The software HDLC decoder will tell me here the large uppercase F tells me flag octet, so that's the beginning of a new message. And then we have 013F EBDF. So the 013F you might remember from the fax printed protocol trace. That's the SABM, the set asynchronous balance mode. This here is just me swapping the bit order because it's easier to look at for me at least. And the EBDF is the CRC16 value that's at the end of the message. Right, and we have the SABM retransmission here again, like we saw in the other protocol trace. We have another one of those messages. This is only one direction that we're looking here, so it's not a bidirectional trace like we got printed from the fax machine, but I'm only looking at one direction of the B channel here, so we only see messages in one direction. And given that we see SABM frames here, it must be the let's say the calling party towards the called party, because that's the one who is sending the SABM frames, initiating the connection. So the session master and initial document master role. The next message we see is this 0100 and so on and so on. I'm not going to read it here. I'm just going to highlight the entire message. And well, the first 2 bytes are basically the header for an X75I frame. And the second 2 bytes, 0100, is the so-called 2-byte block header of the T70 protocol, which is, I think, always 0100. It's not very useful header. And then we have a length byte 09, and we have E0, which is the message type, and TCR is this transport connection request. And later on in the message, we have some additional data. I think the source reference, destination reference, and some more or less TLV encoded additional parameter. And then the 1876 is again the CRC at the end of the message. So we basically see the same, just a bit more raw and with manual decoding that we saw on the fax machine. Here we have some other message that I don't know off my head. 03, I think, is a UI frame in LabD. So here we have the next message, which is again on the X75 layer. It's an information frame. Then we have the 2-byte T70 header, and then we have the TDT with end bit. That means it's a transport data message with the end bit. This is the 80 here set, meaning it's the last message. So it's a not segmented message or the last segment of a segmented message. The 0D here at the next byte tells me it's the command session start message here on the T62 layer. And then we have length octets and some additional values. So here you see the parameter group identifier for session reference with the terminal identifier of the calling terminal with 18 probably as a length value. I'm not entirely sure, or maybe some other indicator. I don't recall the details. But then here again we see the call the calling terminal identifier. So again the 49030650 and so on. So you can see this is a different call. This is one where actually Manam was sending me a fax because it's her number that is in the originating identifier. So yeah, this is how you can decode it by hand. This is of course painful, but in the beginning I really had to get a feeling at all like how is this laid out and how work things. And after looking at this and sort of trying to untangle the specs and what is specified where and doing some manual annotation here, I managed to generate from the raw B channel trace, generate GSM tab encapsulated messages so we can get it into Wireshark. And now I need to find the Wireshark window and move it to the screen. If it's still open, just a second. Is here. No. Once again, too many windows open. Just quickly see if I have. Yeah, no, not. Yeah, there we still have it open. So this is a Wireshark. I guess you can see it. Yes. So this is a Wireshark that contains just some IP packets that on Ethernet headers that are not relevant. Those are just a vehicle to get those messages into Wireshark. In the end, we use the X75 dissector that Manaworm wrote and contributed to Wireshark. So we see here again the two SABM frames, the unnumbered acknowledgement and response. Let's quickly use color coding to differentiate the directions. So I can say colorize, and we do make that yellow also. So now we have, and let's increase the font size a bit if that doesn't work as I'm used to. Okay. So yeah, so here we see the yellow messages are the ones that we transmit, and the blue or whatever light blue background ones are the ones we receive in return. And at the moment, the decoding only goes up to the X75 layer. That's what you have in stock Wireshark. So you can see this is an SABM frame, and this is a UA frame. Well, nice. And here you can see there's actually an iframe that has data in it. It tries to decode it as text, which doesn't make sense here in this context, of course. So what I added is a small additional dissector in Lua, which can decode the payload. No, sorry, wrong. I have to click on this and say decode as. Why is it not working? maybe that's a too old Wireshark window that I opened. I saw there were two in my list of windows. Maybe it was the wrong one. So yeah, this is basically the same trace. Again, I'm going to add the the colorize with filter in yellow to this, so we get the same color coding as before. And now I'm going again to the same packet, which was the first one that contained data. And here, if I decode as, which opens a new window that you cannot see since it's opened at the other end. But if I select the T70 protocol, then we see already some more stuff gets decoded. And here we see TCR and TCA. Those are the messages that we just saw in the T70 layer. So yeah, and you can see my typos also propagating into the dissector here. But yeah, we basically see some very basic decoding of those TCA and TCR messages. And then we see the first data block here, the TDT, which again is just raw data, but it also tries to display it as fax. And we can actually see here also there is some like the header line of the fax or something like that here. RVS fax was set on Manaworm's side, and LaForge is what I said as sort of name on my fax side, and we can also see some timestamps here in ASCII encoding apparently. So yeah, we can see some more data. What's missing here is the T62 decoder. That's what I was working on just ahead of the call. I didn't complete that yet. I can try to instantiate it here, but it probably won't do much other than telling us there is there is a bug in the code. That's as far as I got. But for these kind of protocols where it's very rare and there's very little interest today, it's questionable whether it makes sense to submit and to go through the effort to write a C or develop a C language implementation of a Wireshark dissector, which takes a lot of time due to the long compilation times and development cycles and the general difficulty of low-level C programming. And the alternative that we have in modern Wireshark is to implement this dissector in Lua, which is a nice small scripting language, and it means you don't need to recompile your Wireshark, and also any other user today can just install that Lua file, put it in their Wireshark plugin directory, and not have to compile anything or get a new Wireshark version and benefit from that. So that's why I started this in Lua. I also used this for a number of other dissectors already for very niche protocol use cases where I think it's not really useful to upstream that. And I mean, we could still submit it upstream in Wireshark, so they ship it as examples together with the Wireshark, but not having a C dissector. Also, performance is not relevant for those ultra slow retro networking protocols. So again, Lua is easier to handle in this case. In case you're interested, I will push those to a Git repository shortly. We can have a very quick view about how this looks like. The T70 dissector. So this is just a Lua source code file. Again, it's a script language, so no compilation or anything. So we define a new protocol here. We define what kind of fields we have and what kind of identifiers they get. We define the names of the block types here, as we've just seen, the TCR and TCA, for example. And then we have the function to dissect such a block, where we can extract integer values from the buffer of the network packet, and we can add fields to the Wireshark dissection tree. And we can also call sub-dissectors here. This is where I try to call the T62 dissector from T70 here. And in the end, we have another function that just here, the initialization function that we call during initialization when the file is open. So it's all very simple. Looks very different from, of course, C Wireshark code, but it's rather easy to do and rather easy to test. You just change the file and restart Wireshark, and you see the changes immediately without any compilation or anything like that. So I complete that for T70 and T62, and then soon, hopefully, we'll get proper, more meaningful decodes than just the very first steps I have so far. And that brings us to the end. The raw B channel traces and I think also HDLC hex dumps I've uploaded to a wiki page on the Retro Networking wiki on osmocom.org. So in case anyone wants to dive into this, the traces are there. And as at the Wireshark dissectors, I will commit shortly and also add this information to the G4 fax page on the Retro Networking wiki. And with that, I close the screen share, or maybe, yeah, first I ask for questions. I leave the screen share. Maybe I need to show something in the trace or in the source. Any questions? Or any requests to see anything specific? Maybe an anecdote also in terms of G4. I guess many people will have heard about TIFF G4 before, which is an image file that is used every so often. And it was very popular in digital document archiving some decades ago. And indeed, that uses the G4 image format that was originally specified for use in this G4 ISDN fax. So I guess that has been more popular, this black and white TIFF G4 format, at least before. It's a lossless compression scheme that's highly efficient for black and white images. It's probably more popular than the actual G4 fax system that was ever deployed in ISDN or other networks. So totalizator, not sure how to pronounce it, is asking what my intentions are with this. Well, as with all of this, understand how it's basically digital archaeology, understanding how these protocols and communication systems worked. And ideally, I can't make any promises, but ideally, getting as far as actually having an open source implementation, so we can have a software fax endpoint in open source that can talk to real G4 fax machines over the Octoy network. But yeah, I'm not sure whether I find the time to go all that way. At least the T70 and the T62 protocol I will implement for sure to the extent that's needed in teletext. There I have a stronger interest. It's even more obscure, and I want to get that working. So, and for that I will need the T70 and T62. And then I guess the fact-specific stuff is not all that complex, especially given that we already have open source code for the G4 image format. So I would expect there's not all that much needed once we have these two protocols implemented. And X75 already also exists in open source. So it's, yeah, I guess hopefully later this year or whenever we will have all the building blocks to put together a software implementation. Yes, so indeed, the existing software fax implementations for G4 that we know of are proprietary software. I'm not sure if it's lost knowledge. I would expect at least most or some of the authors to still be among us on the planet and not have passed away. So I'm sure those people are somewhere and maybe they remember things. But in terms of source code, I did not find any open source G4 softfax implementation. You can find G3 for analog fax. Of course, there's Hylafax and other implementations. mGetty plus SendFax, which, well, okay, they speak AT commands, so they also don't implement everything down to the last a bit, but with fan DSP and so on, you can have an actual true G3 software fax implementation, all in open source. There was a question or more comment that it appears there's no intent of interoperability between G3 and G4. Yes, that was the case, but it was also the case between G1 and G2 and G2 and G3. Those all are different systems, and there's no forward-backward compatibility, at least not that I have heard of. Christoph Lauter is typing, so maybe I commented something wrong, and I will stand corrected shortly. But yeah, those are completely different systems, at least G3 and G4 definitely, and no interoperability whatsoever. Okay, yeah. So apparently some G2 devices had G2 backwards compatibility. Okay. I stand corrected in that regard. But yeah, the same is true for G4 devices. But I mean, in a sense that, let's say a G3 device is compatible to G2 because the G3 device actually is a combined G3 and G2 device. I don't think there's much that is like in the G3 protocol or system. There's nothing that sort of has this backwards compatibility. It's just that the manufacturer decided to implement both standards in one device, which is, by the way, the same for my physical Canon L260i fax machine, which also implements G3 and G4. G3 and G4. So I can make an ISD actually, and there's an automatic fallback. So when it tries to send a fax, it will first try to send it as a G4. It tries to make the digital call with unrestricted digital information bearer type. And if that fails or is rejected, then it falls back to doing a 3.1 kilohertz analog call and has a soft modem built inside to do an analog G3 fax transmission to the remote end. But yeah, it's just that the device implements two different systems and it's not a compatibility in the protocol itself in any way. Well, I mean, it's there's a comment that lay people think fax is universally interoperable. Yeah, well, that's, you know, lay people think all kinds of things. Yeah, it's what can I say to that? Yeah. There was a question if anyone could share published a wiki list of known G4 fax machines. Well, I personally know only two of them. One is this. Well, actually, three. Yeah, I will add a couple of things to the wiki, but the L260i is sort of yeah, one that was guaranteed to be included because it was always included from the factory. There is an L1000 from Canon where ISDN is an option. If it's installed or not depends on whether somebody installed that option. And there is a T-Fax 360 ISDN G4. And you need to make sure that it's exactly this name, because if it's only ISDN and not the G4, then it is exactly what it claims. It's an ISDN capable fax without G4 capability. So yeah, but yeah, we'll add that to the list. So I've had basically all of the known models in my eBay and other related site search terms, and I guess you see one of them every year or every 2 years. So they're very rare to show up. Okay, then I guess we can close the recording and switch back to the general chat. Thanks everyone for your attention and interest, and yeah, hope to see you soon at a future RetroNet call.